animating hundreds of characters in Unity without melting your CPU. Hello and welcome to episode number 17 of the Unity Performance Task Force podcast. I'm your host Ruben from TheGameDev.Guru, and as usual I'll kick things off with a question for you. Have you ever tried to put a few dozen animated characters on screen and watch your frame rate drop like a stone? Maybe you're building a football stadium crowd, a city builder with pedestrians, or a racing game with NPCs, and suddenly your CPU is screaming for mercy at just 50 characters? Sounds familiar? If so, this episode is for you. Today we're tackling one of the most requested topics in the backlog: how to animate hundreds or even thousands of characters without destroying your performance budget. Fair warning up front, this is one of the most complicated areas in game development. There are entire research papers dedicated to this problem. So I'm not going to sugarcoat it. This is hard. But I'll give you a clear mental map of your options, the trade-offs, and practical next steps. Let's start with the why. Why would you even need so many characters? Well, it depends on your game. Maybe you're building a sports title like FIFA where the crowd needs to feel alive. Maybe you're creating a VR driving simulator with realistic pedestrian traffic. City builders need believable foot traffic. Racing games, especially the chaotic ones, might have crowds you can actually hit. And sometimes the answer is simply, why not? Your creative vision might demand it. But here's the problem. By default, Unity is not built for this. Skinned mesh renderers don't batch out of the box. The animator component, while powerful, carries significant CPU overhead because it supports state machines, blend trees, and complex transitions. And skinning itself, transforming vertices based on bone positions, is expensive whether you do it on the CPU or GPU. On top of that, draw calls can kill you fast. If you're targeting quests with a budget of 200 draw calls, you might hit your ceiling at 200 characters, and that's before rendering anything else in your scene. On the GPU side, vertex count adds up quickly. If each character has 3,000 triangles, and that's on the low end, 100 characters puts you at 300,000 triangles. Skinning on the GPU is generally better than CPU skinning, but it still costs you. So what can you do? I've grouped the solutions into 4 categories. First, GPU skinning. Second, dots animation using Unity's com.unity.animation package. Third, skipping skinned mesh renderers entirely with techniques like animation instancing or image-based rendering. And fourth, complementary techniques like LODs, reducing bone influences, and using legacy animation systems. Keep in mind you'll likely combine several of these approaches. This isn't an either-or situation. Let's start with the easiest win, GPU skinning. Skinning is all about transforming vertices based on your skeleton's bone positions. Traditionally this happens on the CPU, but modern GPUs are way better at parallel computation, so just move it to the GPU. In Unity you enable this in player settings under Other Settings. Look for the option called Compute Skinning and turn it on. It's supported on DirectX 11 and up, OpenGL ES 3.1, Xbox One, PlayStation 4, Nintendo Switch, and Vulkan. I've used this extensively on Oculus Quest, which supports OpenGL ES 3.1, and the CPU savings are substantial. I've seen meaningful improvements with as few as 4 characters. This doesn't help with draw calls or animator overhead, but it frees up your CPU, which is often your main bottleneck. Just enable it, profile it, and measure the gains. Simple as that. Next up, dots animation. This is Unity's com.unity.animation package, available on GitHub with examples. Big disclaimer, this is highly experimental. The tooling is sparse. You'll be writing a lot of code. There's some UI work in progress, but it's not documented well, and you will pull your hair out. This is designed for URP and HDRP. If you need the built-in render pipeline, you're on your own. But if you can stomach the learning curve, the payoff is real. You reduce animator overhead, increase parallelism in animation post-computation, and you get to reuse modular nodes. These nodes are just pieces of code with inputs and outputs. Unity provides nodes for 1D and 2D blending, playing animation clips, and you can write your own. You connect these nodes in a data flow graph, pass data through, and get your final animated pose. The terminology gets fancy fast. Data streams, messages, ports, kernels. Expect at least 10 hours to get up to speed if you're comfortable with animation systems. If you're new, budget 20 to 30 hours. Start with the data flow graph documentation and guided tour, examples A through K. Once you understand kernels, nodes, and message passing, move on to the animation-specific samples. Some are HDRP only, but you can port them to URP yourself. This is the exact pattern we use at TheGameDev.Guru when teams need to scale animation beyond what Mechanim can handle. The upfront cost is real, but the runtime performance is worth it if you're serious about crowds. Now let's talk about the nuclear option, skipping skinned mesh renders altogether. Why? Because they don't batch and animators are expensive. Instead, you use mesh renderers or even sprites. This is harder than it sounds, but it gives you massive CPU savings and reduces draw calls. There are two main approaches here. First, animation instancing. The idea is to bake your animation into texture data. For each frame of your animation, you store the vertex positions in a texture. Each row might represent one frame, and each column represents a vertex position. Then in your vertex shader, you sample this texture and transform the mesh on the GPU. This shifts almost all the work off the CPU. You reduce draw calls because you're using mesh renderers which can batch or be instanced, and you bypass the animator entirely. The benefits are huge. Big CPU boost, fewer draw calls, no animator overhead. But the problems are also huge. It's hard and time intensive. The pipeline is complex, you lose blending, transitions, root motion, inverse kinematics, and most animator features. You'll need to rebuild what you need from scratch. It's not a one-size-fits-all solution. You might need different implementations for different levels or character types. Variability is tricky, you'll need shader tricks to randomize animation offsets or playback speeds, and memory usage can balloon because you're storing vertex positions in textures. The more frames, the more clips, the more memory you need. I've included a free GitHub example in the resources that demonstrates this. You'll see hundreds of characters animated using mesh renderers and an animation map texture. The texture looks like noise because it's storing positions, not colors. In the shader, you sample this texture based on the animation frame and vertex ID, and you get the final position. I've added some variability by using the instance ID to offset the animation playback. It works, but expect to code everything yourself. Blending, you code it. Transitions, you code it. IK, good luck. There are paid assets on the Unity Asset Store that handle some of this for you, but read the fine print. Check platform support and feature limitations before you buy. I'm not recommending any specific asset, just pointing you in the right direction. The second approach is image-based rendering. This is where you render 3D characters as 2D sprites or quads. You animate one 3D character traditionally, render it to a texture using a camera and render texture, and then draw that texture many times across your scene using sprite renderers or quads. This is mostly useful for background crowds where detail and interactivity don't matter much. The performance gain is enormous. Rendering 2D is way cheaper than 3D, and you skip all the animator overhead. Setup is relatively easy, but the characters look flat, because they are. If they rotate, players will notice. This works great for stadium crowds where characters are tightly grouped and distant, but you lose variability unless you render multiple characters and randomize which texture you display. Lighting and shadows are tricky, you might get away with blob shadows or no shadows at all, and be careful with overdraw. If your quad is mostly transparent pixels, you're wasting GPU time. You might need custom meshes with tighter UVs to reduce overdraw. I walked through a quick example where I set up a render texture, a camera rendering a 3D character to that texture, and a quad displaying the result. You can duplicate that quad hundreds of times. If you angle the camera slightly and use billboards, the flatness is less obvious. But you'll need shader work for color variation, possibly masking textures, and careful culling setup. Prototyping is critical here. Build a quick proof of concept, measure it, and decide if the trade-offs work for your game. Now let's talk about the complementary techniques. These work alongside the approaches I just covered. First, LODs. Level of detail isn't just about reducing vertex count for the GPU. Fewer vertices also mean cheaper skinning. Use aggressive LODs for distant characters. Second, reduce the maximum bone influences per vertex. The default is 4, which works for humanoids, but if you can drop to 2, do it. The quality hit is often negligible and the performance gain is real. Third, consider the legacy animation system if you don't need Mechanim's features. It's less flexible, but it's faster. So when should you actually care about this? When you hit a bottleneck. On high-end PC, you might not see issues until 100 or 300 characters. On Quest or mobile, you might struggle with 20. In my experience on mobile, performance degradation starts around 3 to 5 characters if they're complex. Profile early, measure often. Let me be clear about something. All of these techniques trade performance for flexibility and feature set. You will lose things you're used to. Blending, transitions, root motion, inverse kinematics. Some techniques let you rebuild these features, but it takes weeks or months. Unity doesn't provide this out of the box because it's genuinely hard and very use case specific. They build for universality, and a solution that only works for 1% of projects isn't good business. So yes, this is going to be time intensive. You're going to write custom tools, you're going to iterate, you're going to test and throw things away, but if your vision demands hundreds of characters, this is the cost. Before we wrap up, let's talk about the objections you're probably thinking. First, what if I need interactivity? Image-based rendering won't cut it. You'll need animation instancing or dots. Second, what if I need inverse kinematics for foot placement? You'll need to implement it yourself if you go the instancing route, or stick with dots and see if Unity's IK nodes cover your needs. Third, what if my animation clips have tons of frames? Memory will be a problem with texture-based approaches. You might need to reduce frame rates, compress textures, or use dots instead. Here's your action plan. First, enable GPU skinning if your platform supports it. This is the easiest win. Profile it and measure the CPU savings. Second, if you need more than 50 to 100 characters, start prototyping. Pick one approach, build a minimal test scene, and measure draw calls, frame time, and memory. Use the same characters and animations you'll actually ship. Third, if GPU skinning and LODs aren't enough, evaluate dots animation. Budget time to learn it. Start with a guided tour and examples. If dots feels too experimental or your team doesn't have the bandwidth, look at animation instancing or image-based rendering. Fourth, if you go the instancing or image-based route, identify which animator features you actually need. Make a list. Blending, transitions, root motion, IK, then research whether the asset or technique you're considering supports them. Finally, combine techniques. Use image-based rendering for distant crowds, animation instancing for mid-range characters, and full-skinned mesh renderers with GPU skinning for close-up heroes. Let's recap. To animate hundreds or thousands of characters in Unity, you have 4 main paths. GPU skinning for easy CPU savings, dots animation for parallelism and reduced animator overhead, skipping skinned mesh renderers with animation instancing or image-based rendering, and complementary tricks like LODs, reduced bone influences, and legacy animation. The best results come from combining these, but expect to invest serious time. This is one of the hardest problems in real-time rendering, and there's no magic bullet. Prototype early, measure constantly, and be honest about what features you actually need. If you found this podcast episode useful, you can access in-depth lessons in the Unity Performance Task Force program at www.performancetaskforce.com. And if Unity Consulting is what you are after, book a free discovery call at https://consulting.thegamedev.guru. Till next time.